Welcome back, students. In this video, we are going to look at Sn1 and Sn2 practice problems. Here's a typical Sn1, Sn2 practice problem. I want us to be able to predict if this is going to be an Sn1 or an Sn2 mechanism, and then figure out what the product is going to be, or products. If there's no reaction, we would just go ahead and say no reaction. I want to lead you through the logic that we went through in the last video, where we looked at those 4 different factors, but now I want to actually show you how to use those 4 factors. I always like to start first with my substrate. The substrate here, remember, is your electrophile. And your substrate has that iodine, which is your leaving group, and it's attached to this carbon. That makes this a secondary substrate. Remember from the last video, we said that secondary substrates could go either through Sn1 mechanisms or Sn2 mechanisms, so this alone is not going to tell us which mechanism is going to occur. Then let's also check our leaving group. We're happy that we have a good leaving group, but it doesn't tell us which mechanism is going to predominate. So we're just going to make sure that we know that we have a good leaving group, because if we didn't have a good leaving group, then the reaction would not occur. Then over the reaction arrow is water. This is a type of reaction called a Sovolysis reaction, which is where your solvent and your nucleophile are the same thing. The water is going to be both our solvent and our nucleophile. We call that, one more time, let's write it down, a Sovolysis reaction. Your water is a polar protic solvent, and it is a weak nucleophile. The fact that we have a weak nucleophile helps point us towards Sn1 because Sn2 tends to use stronger nucleophiles, but then our deciding factor is going to be the solvent. Whenever you have characteristics that are not strongly pointing one direction or another, the solvent is going to play a much more important role than you realize. I think a lot of times students disregard the solvent, but we don't want to do that. The solvent really is going to matter. Our polar protic solvents are going to determine that this is an Sn1 mechanism. So we know this is Sn1. Now let's remind ourselves what happens in our Sn1 mechanism. The leaving group leaves, we create a carbocation. We're watching for potential carbocation rearrangements, and then our nucleophile adds. You could practice drawing the full mechanism for this because you are perfectly capable of doing that. Right now I'm just going to predict products. In my head, I just want to show you what goes on. So that this is my brain. In my brain, I'm remembering that when the iodide leaves, I form a carbocation there. I need to look at that and ask myself, can this rearrange to form a more stable carbocation? And the answer is no. I know what you're looking at. I know that you're looking right here where I highlighted in blue thinking, can I get that positive charge there? No, you cannot. You cannot, because you can only go to an adjacent carbon. Okay, there's no hopping. You're not leapfrogs. So I've mentally drawn my carbocation. I've decided that there's no possible carbocation rearrangement. Where I have that carbocation is where my nucleophile is going to add. I'm going to redraw my structure. And here where I'm drawing that green dot is where my nucleophile is going to add. Remember that water is the nucleophile. When water adds, and I'm going to erase what's happening in my brain over here. When water adds, it's going to add like this first, but then that extra proton is going to get taken up, so we're going to get rid of that. You can do that in the mechanism, right? So it's not the H2O that's adding, it's just the OH that ends up adding. So we got an alcohol here. Now, because nothing happened at that other side of the molecule, the chirality on the other side of the molecule that I'll highlight in blue, that stays the same, right? That doesn't change. On our SN1, we get inversion and retention of configuration. I've drawn retention of configuration where I had an iodide was wedge, and it's still wedge. Now I need to draw that OH on a dash in order to show inversion of configuration. The wedge for the methyl stays the same. No reaction happened there, so that's not changing. In this case, you would want to indicate that you have a racemic mixture. Remember that it's not actually perfectly racemic, but if you're in my class, we're just calling it racemic. If you are in someone else's class, you just want to be aware that they might want you to know that this is not perfectly racemic because of when the iodide leaves, it hangs out close by to the carbocation for a moment. It creates something called an ion pair that prevents the retention of configuration from happening. So, but it's close enough to racemic. I'm calling it racemic. Let's try another one. In this one, I'm going to go through and do the same type of thing. Let's look at our substrate first. I find where my leaving group is attached. This is a secondary substrate. My leaving group is that iodine. It's a good leaving group. I'm going to abbreviate leaving group as LG. Your Cn-, if we go back to our table of strong nucleophiles and weak nucleophiles, this one's a strong one. I'm going to abbreviate nucleophile as NUC. For THF, this is a polar aprotic solvent. Now that we've labeled all of these, let's figure out what the mechanism is going to be. We have a good leaving group, great. That means a reaction is going to happen. We have a secondary substrate, not helpful because that just tells us that we could have either, right? SN1 can be secondary, SN2 can be secondary. Then we have a strong nucleophile. Strong nucleophiles tend toward SN2 mechanisms. And then the polar aprotic solvent, deciding factor. Aprotic solvents go toward SN2 mechanisms. So this one is going to be SN2. Remember that your SN2 mechanisms undergo inversion of configuration. What that means for us is when we draw our final product, we are going to see that the iodide was on a dash and all of our product will be on a wedge. We can then take our carbon of our cyanide, I'm just going to draw this really quick to show you that the carbon is the more nucleophilic part of this. And so the carbon is going to add, and you're going to get that cyanide ion on there. You could also draw this with that triple bond still. The reason I didn't is because you're probably going to accidentally forget that it's linear and you're not going to draw it like this. And that's how it should be drawn to illustrate that the carbon nitrogen is a linear aspect to that molecule. So you're going to get full inversion of configuration in this SN2 reaction. All right, final one. Here, I want to go through and do the same thing and look at our substrates, then look at our nucleophiles and so on. We've got bromine, which is a good leaving group. H2S is a strong nucleophile. This one is your solvent. This is acetonitrile. This is an aprotic solvent. Those are the things that you're going to have to memorize, right? You're going to have to know what I had in those charts. And then once you have those things memorized, then you have to practice applying them, right? So we're memorizing a bit of information and then we're doing practice applying. I also need to look at the substrate. This substrate is unusual in the sense that everything here is pointing toward an SN2 reaction, but you know what? Where the bromine is attached, the carbon that I just highlighted, that's an sp2 hybridized carbon. And you can't have an SN2 reaction happen in an sp2 hybridized carbon because there's no possibility of the inversion of configuration to occur. So there's two things to look at here. If this were SN1, you still wouldn't have this happen, right? This one is called an aryl structure, where you have the leaving group directly attached to that benzene ring. It plays tricks on you because you feel like it's vinylic or going to be a vinylic alkyl halide, but it's not, right? So it tricks your eyeball. This is not going to be a reactive compound for SN2 or SN1. It's not reactive for SN2 because that sp2 carbon, because you have an sp2 hybridized carbon where the bromine is attached. And you cannot have inversion of configuration if you don't have an sp3 hybridized carbon. So there's no reaction for SN2 because you have an sp2 hybrid reaction center. If it were an SN1 reaction, you still wouldn't have that be able to occur because you can't form an aryl carbocation. They're not stable. So do watch out for the things that are no reaction. Here I have the same wrap up as I did in the last video to remind you of what you're looking for. You're looking for your substrate, your nucleophile, your leaving group, and your solvent, and you're taking all those pieces, you're putting them together and figuring out which mechanism is going to occur. Thanks so much for watching and keep practicing. I know this stuff is hard, but keep trying it. You're going to do great. This is Katoni signing out.